Hi, my name is Steven,
And my name is Jade,
and we are part of Physics Filmmakers.
2016 to 2017. We're second year undergraduates and
We are studying physics and astronomy, and today we are going to be recording inside F12, UCL Underground Laboratory.
enjoy!
Thanks for letting us film film some of your work here in Underground Labs. Could you introduce yourself to our audience, Michela?
Yeah, I'm Michela. I'm a third year PhD student in physics here at UCL, and this is the experiment I've been working on for the past 3 years now. This experiment is about ultracold atoms, and when I said ultracold, I mean atoms are with a temperature around tens of nanokelvin, so very cold atoms. In this experiment we work with rubidium-87 atoms, and what we do is to cool the atoms from room temperature till very low temperature. Indeed, I'm speaking about tens of nanokelvin. And what we want to achieve is to obtain a reliable Bose-Einstein condensate, which is a particular state of matter. So all the atoms are in the lowest energy state of the system, and what we want to do with this experiment is to study the dynamics of these ultracold atoms into an optical lattice. So we want to study how the atoms behave when they are trapped into two counter-propagating laser beam, and we want to see how their behavior change while we vary the parameters of these two lasers. We achieve this particular state of matter by using a technique called laser cooling. With the laser cooling, we use the light pressure to cool the atoms. And for cooling, I mean to decrease the kinetic energy of the atom.
All the black boards you can see around the experiment are to prevent stray photons from exciting the cooled rubidium atoms. That's how delicate the experiment is.
What's really cool is that atoms are cooled from room temperature to nanokelvin in just 1 minute and 10 seconds. Michela only has 25 milliseconds to study them before they warm back up, so she uses a high-speed camera to observe what is happening within the atom cloud in the block.
The cooling occurs in stages. The first is a magnetic optical trap, which cools the atoms down to several microkelvin. Now these are produced by two anti-Helmholtz coils, which sets up the magnetic field gradient.
An atom is then excited and is then pushed with a circularly polarised laser beam of a very specific frequency. Moving the atom this way with light is like changing the momentum of an asteroid by throwing billions of ping pong balls at it each second.
This occurs in the X, Y and Z axis to place the atoms in a particular position. By slowing down the atom, we reduce its overall energy, and kinetic energy is related to the temperature with this equation, where V is the velocity, M is the mass of the particle, T is the temperature, and K is a constant.
Okay, next we move the atoms with laser beams to a second chamber with an ultra-high vacuum. We do this otherwise background atoms will collide with our ultra-cold atoms and cause them to gain energy. Here there are multiple stages. The first is another magnetic optical trap.
The second stage is subdoppler cooling, which then cools the atom down to tens of microkelvin. Then we have a magnetic trap, which traps the atoms to the bottom of a cone-shaped trap.
Once the atoms are trapped at the bottom of this, we then apply what's known as a dipole trap. This consists of two powerful 20-watt lasers which cross over and exert a force on the atoms, causing them to be trapped inside the laser.
The final stage is the evaporation process, which occurs in the magnetic and dipole trap. How it works can be explained in a very basic analogy with a boiling cup of water. The hotter, more energetic particles will evaporate and escape at the surface, leaving the cooler atoms at the bottom of the boiling cup of water, or the magnetic trap in this case.
By losing the molecules with higher temperatures, the average kinetic energy goes down. And there we have it, a Bose-Einstein condensate. From about 3 million rubidium atoms, only about 50,000 make it to the Bose-Einstein condensate level.
The speed of the atoms are then calculated by how fast the atom clouds expand. Okay, thank you for watching our video, and a massive thank you to Michela for allowing us to film some of her work.
Here are some bloopers for y'all.
Yo.
Yo.
What are you doing?
Alright, we're recording. I was
Oh.
just adjusting the focus.
Hello. I'm Jade.
And we are part of Physics Filmmakers.
Wait, can we try that again?
Yeah.
Thank you. Do we just appear? Jade?
We are part of Physics Filmmakers.
2017. No,
2007.
2016.
2000.
Okay, I think